All right, let's start. Hello, everyone. This is Dr. Yuzo, ECE 341 Power System class. And today is our 17th lecture, and we are at week 9, Wednesday. So after today, obviously, this week is basically done for this course, at least. And first of all, can you guys hear me well?
Yep.
All right, thank you. All right, then we're going to move on. So first of all, here is what we learned from last lecture. Okay. The Lagrange multiplier, which is a total function trying to combining f and the g's. Of course, who is f? And who are the g's? Anyone remember? Who is f?
Was it the objective function?
Objective function. Very good. Very good. Okay, Noah is right. The objective function. And g's are what?
Constraint function.
Constraint functions, right? Actually, by writing in this way, we are basically only talking about the equality constraint. But it's very easy for you to understand that if involving inequality constraints, what we should do, right? So for example, objective function f of x1 through xn. Equality constraint are g1 through gk, right? They all function of x1 through xn as well. By equality, it means what? There are equations, right? Equals to 0 eventually. But inequality constraint are also possible, obviously. We can differentiate them from the equality constraint by using different letter. We can use different letter. We can use U1 up to U. Well, next need to be different as well. So, right, it's not necessarily the same number as the equality constraint. So subscript here could be up to m. I just assume up to m. But independent variables remain same. Right. So it's actually very straightforward that when we develop this total Lagrange multiplier, just as simple as this. Once again, combining f and the g's and the u's, right? The g's we remain using the lambda 1 through lambda k. This is what we did in previous lecture already. Right? Now it's very natural. We are introducing different constants. Lambda, say lambda 1, u1 add up to lambda m and um. So this is a new Lagrange multiplier, including the objective function, equality constraints, and the inequality constraints. It's very straightforward. And of course, Let's go through one example so you know how to solve this by applying the L function. This is not difficult, but let's see. Okay. Example 2. Just this. Example 2. Very nice that objective function is given as x squared plus y squared. And the subject to constraints. First one is x minus minus 6. And very straightforward. We don't need to identify who is whom, right? It's already clarified. Objective function is x squared plus y squared. The constraint functions include one equality and one inequality, right? So obviously, f is x squared plus y squared. G is what? This is just like what we did in previous lecture. You move 25 to the left-hand side of the equal. So it equals 0. U is what? Right. So after having these three, everything is very straightforward. Total function is equals to f plus lambda times g. We don't need any subscripts since we only have one g and one u, right? So lambda times g, then plus what? According to what we have here. Alpha, right? The newly introduced constant is alpha. Alpha here times u, which is 2x plus y minus 12. So what's the next? Anyone remember what we should do next?
Second partial derivative.
Very good. 2 is right. Okay, start to find the partial derivative. So we at least need partial derivative of x, partial derivative with respect to y, partial derivative with respect to lambda, and partial derivative of alpha. So 4 simultaneous equations to solve at least x and y. Because the problem is we probably don't have to find out the alpha and lambda. We probably don't have to. Because obviously the problem asking the minimum or max value of this guy, right? Subject to these two things. So lambda and alpha values are what? Not something useful, right? Not something useful. So I'll give you guys 2 to 3 minutes to write the equations. to write equations as exercise. Find the partial derivative. Go ahead. All right, let's see the 4 equations together. So it's not difficult, but don't make a mistake. Okay. So these are the equations. And take a look at these equations. Any idea about algebra? Because remember, going back to example 1, we had to take care of the product between 2 unknowns. And that's very troublesome. So I came up with a idea to do a division to cancel one of the unknown. But here, what can you see here? How to solve these equations? The easiest way, of course. Well, let's see back. Yeah, well, if your calculator is really that powerful, then, well, yeah, maybe I should sit back too. But
Would we start with alpha equation?
Start with what?
The bottom alpha equation?
That's right. Okay, actually, both Sawyer and Anil saw this thing. So basically, what you're seeing is just to substitute this guy into here, right? I mean, you can substitute either x or y, and then done. Ignoring first equation, then second equation. How about that? I think this is the easiest way. Once again, you find out maybe y in terms of x from the last bottom equation, and then substitute that y here by this derived y equation. Right? In other words, this guy can give you y equals to 12 minus 2x. And then substitute y here by this guy. And if you conduct this calculation by using the very last two equations only, then you should end up with this. And then from here, you got x value, quadratic equation. Anyone got anyone? Maybe not. It's fine. 3.5. And correspondingly, you got y value 6 and 2 respectively. Two sets of solutions. And of course, not done yet. They respectively going to give you f m1 equals to and f m2 equals to. This is 45. This is 29. Okay. That makes sense. Any questions regarding this problem? Yeah, we're done here. Yeah, we find the minimum value, which is obviously this guy. Minimum value. Okay, we are looking for the smaller one between these two to find the minimum value. So which the other one is not necessarily the maximum value. Let me explain this problem in this way. Okay. Problem in this way. Put this problem here. How to visualize this guy, just like we did last lecture. It's still what, circle, right? Still a circle, actually. Still a circle we are seeing. Y axis, x axis. So first of all, you're seeing the same circle at, let me see, 8 and 6. So let's assume this is 8. And this is 12. 8, 6. This is 6. I'm sorry, it's a 4. It's a 4. This is 6, 2, 0. Okay. And then you have 8 and the 6. So the center point of the circle is right here. Is once again coordinate 8 and 6 with radius 5. Radius 5. So this guy is. This is 1/4 of the circle. That's 1/4 of the circle. Don't have to finish the entire circle, but this is a circle, which is our equality constraint. Makes sense. And f is what? Is you can feel free to understand this like the example 1, which is the distance between what, origin point and this circle. And then how the inequality constraint kick in then. Is that clear? First of all, the inequality constraint function is a what? Anyone can tell. This is what? once again, we're trying to visualize the problem here. So anyone can tell what this inequality constraint, what is it?
For this circle is on the x-axis, is that supposed to be 3? Or isn't the radius 5?
Yeah, it's 5. So
Okay. I mean, is that a 4, 8, and a 12? It looks like the radius is 4 there.
no. 4 is here. So here is 3.
Oh.
Does it make sense?
Yeah.
Yeah. So and from here to here is obviously because here is 1. 6 to 1 is 5. Right? So once again, this here is the end, which is 1. Here is 3 here. Right? This is how we see this. And going back to the question, so how we see this guy, this inequality, and then how to visualize this guy.
We want to shade the area of what we're trying to achieve.
Exactly. So the John's point is by here is a shape of a area. However, which area? How to find that area? Obviously, this is something you need to above certain thing, and then that area is this, right? But how to find that area?
So we can just solve for y, and then
Get the slope.
that's going to give us the line. Yeah, and then we can.
That's right. Okay, that's right. Good. So basically, the point is, what do you see here? There's 2x plus y minus 2. If we are thinking of 2x plus y minus 12 equals to 0, what is this? It's line, right? It's straight line. It's straight line. So how to find a straight line in the picture? It is here, right? Now let me use a blue color too. So when y is equals to 0, x is 6. Okay. When x equals 0, y is equals to 12. Oh my. See the problem? 12 is basically here, right? If I'm extending the y-axis. Does it make sense? Yep. So this distance is basically same as this distance, right? Is it clear what I'm doing here? No response. I'm gonna take that as yes. Then if this is 12, then you're connecting these 2 points, right? What I'm doing is I'm selecting 2 particular points because 2 points are enough to determine one line. That's why I'm determining 2 particular lines. Therefore, further to determine this line, okay, intersecting with the circle, intersecting with the circle. So the next thing is how to make this happen. We just discussed that this is a shade, right? Shading that area. So this means what? Above this line, right? Above this line. What does it mean by above this line? How about just this shade? So inside of this shade area, and also there must be on the circle. So here we should say the distance between the origin point and the circle within the shaded area. Right? Does it make sense? This is the description of the objective function, right? We're trying to look for the minimum distance of it. Does it make some sense? Any questions?
Yeah, so does that mean that when we're doing another problem of these later in the future, do we only shade inside of the circle, or do we also just do the lines like that to show what part's shaded?
Well, you shade this, which part is all above to here. Greater or equal than 0, then it meaning this area. Has nothing to do with the circle yet. Okay, the inequality constraint function itself is independent of any other constraint function.
Okay, gotcha.
Yep, it has nothing to do with circle. We just read the problem here from here. If this is less and equals than 0, then we are shading here. Is that? So it has nothing to do with circle.
Okay, thank you.
Sure. And then from here we are looking for the minimum value of the distance. Where is the minimum value of distance? Going back to example 1, in where we didn't have this inequality constraint. The minimum value is here, right? Does it make sense? Basically this point. Now, this point is obviously not inside of this area, right? So how to find the new minimum value? That's why we have different answer here. That's why if you check, we have different answer, different coordinates point to make this minimum f happen, right? So from here, you can see either here, intersection point here, or intersection point here. Does it make sense? Either here or here. Does it make sense? It couldn't be anywhere else because we are looking for the minimum distance, right? So either here or here. And turn out that they are 3 and 6 coordinates and 5 and 2. This is 3 and 6. This point is 5 and 2. Compare this to distance, and this is smaller. So this is the solution. The miss in viralized graphs. Well, actually, this graph is not required. Okay, if you are have a little bit hard time to viralize this graph, that's not a big deal, because this problem is not asking for this viralized graph. No, it's not asking for the explanation in terms of graph. No, I'm just presenting it to help you understand the how it makes sense. Here, Sawyer is asking a square root of 29. Yeah, Kevin is trying to explain actually, because don't forget, our specified objective function at the beginning is x squared plus y squared, rather than distance. Be very careful. Who is the objective function? In this example too, objective function is not distance. It's as x squared plus y squared. So 29 is the x squared plus y squared minimum value. And that's why we are done. And And we find two local minimum value, M1, FM1, and FM2. By comparison between them, we find the global minimum, 29. And from here, this graph, it makes perfect sense. See any questions, any concerns?
So with the x squared and the y squared, right?
Mm-hmm.
Originally we did that. We removed the square root, and then we squared, or we square rooted the answer afterwards.
Yes, yes.
So is that what we would do in this problem? Like, that's not the final answer, or no? Is it?
Like I said, your objective function this time is not square root.
Oh, okay. Okay.
Right. Yeah. Your example one, you take a look at it. The objective function is square root. So it's all up to what objective function you have, basically. Here it's not asking for square root, so we don't do square root. Here I have a question received. What does the global minimum mean? The global minimum means, going back to previous lecture, we have multiple local minimum and maximum values. But global means this guy is obviously global one, right? Because it's the lowest, is the minimum, rather than one of the minimum, or say one of the lowest. Okay. This is a local one. One of the lowest. However, among those lowest ones, you find the lowest. The lowest. That's the global minimum or maximum. And here, local maximum, local one. And this obviously is the global one. All right. Any other questions? Any concerns? Not very difficult. I don't think so. Just.
And we can assume that the higher value is a global maximum. We can only say that it's just a maximum or nothing at all.
A higher value, which is 45 here?
Yeah.
No, like I said, 45 is here. Another local minimum.
Okay.
Yeah, we can't assume it's maximum or by this graph, it's another local minimum, actually. By the way, who is the maximum? In this graph, who is the maximum?
The maximum would be all the way to the end of the other circle, wouldn't it?
Yeah, then how to end to the circle? We need to go through, have a line go through the center point and then reach the other end of the circle, which is this point, right? Does it make sense? This is the maximum distance, or say the maximum value for x squared plus y squared. Does it make sense, everybody? And here, what does the x and the y stand for in the real world? Well, this is a very big question. Here, if you only think of the math, they're just one is independent variable, another is dependent variable. In the real world, it could stand for anything. Right? Yes, math could be applied onto any real applications. Real world standing for, well, you can think this is a ball. This is a ball, a circle ball. And then you have a line here, and then you're standing at the origin point, and then you're trying to reach the line as well as the circle. What's the minimum distance in terms of the power system? Oh, that's the question. That makes more sense. That question makes more sense, actually. Not in real world, is in terms of the power system course. No, it's not related to the power generation optimal dispatch yet. Okay. Because in the optimal dispatch, we will learn what is the cost function. Right? The cost function should be given at first place. And then we will figure who is the constraint functions, and then applying the same procedure and idea, which is the mathematical method, to solve that minimum value for the cost function. So by then, the cost function is our particular objective function to study. This is how is this math related to the power system, power generation. These things, no, has nothing to do with it. Here it's just trying to help you understand this math. Help you understand the math. Any other questions? All right, then do one exercise completely by yourself. Once again, now you just need some exercise, and then you should be ready for the exam. Objective function is given as subject to constraints x squared minus 5x minus y squared plus 20 equals 0. U equals to 2x plus y greater than 6. Find the minimum value of f. No, it's not difficult at all, but you need to do exercise. All right, I gave you guys 5 to 8 minutes. Should be enough. All right, go ahead. All right, folks. Seems you have already got the correct answer. So let's go over it really quick. So the procedure is as simple as L equals to S squared plus Y squared plus lambda 5x minus Y plus 20 alpha x plus Y minus 6. And then you have our x partial derivative to every single one of them. Right, so 4 equations, and then respectively 2x plus lambda x minus 5 lambda 2 alpha 2y minus 2 lambda y alpha and then here we have x squared minus 5x plus 20. Here is x plus y minus 6. 0, 0, and 0. Right? So once again, you can just use these two equations to find x and y value, respectively. You got once again 2 sets, 1 of 4 and 16 third and negative 14 third. And here, going to give you fm1 equals to this, going to give you fm2 equals to, eventually you got 17 here, and this number is bigger, 50.22. That's the solution. Okay. And hopefully it will be as smooth as this time in the exam. Not only give you 15 out of 15, but also save you a lot of time, right? So on the easy problem, you don't want to spend more than, say, 10 minutes. Okay. All right. Any questions? Any concerns? All right, if no questions, let me ask you one. Once again, go back to example 2. Once again, go back to example 2. Let me ask you this. What are we going to do if this problem is this way? Instead of greater or equal, it is less or equal than 12. What are you going to do? Anyone, any idea?
Shaded downward.
Say that again. 2.
You would shade the graph other way.
Good. Okay. 2 is right. I'm going to shade this way. So tell me, what is the answer? Looking for the minimum value, minimum distance, once again. Same question. Then what is the answer this time? Anyone knows? What is the answer? Oh, very good. Oh, very good. Very good. Very, very good. Okay. Very, very good. Obviously, both Kevin and Sawyer see the thing. So Kevin's description is very high level answer. It's a very good. Excellent. It's not only answering the question, but also telling you how. Okay. So Kevin is saying ignore the inequality and do just the F and G. Can everybody follow this? In other words, if the problem give you that like this, you're gonna do the same. However, this is a tricky question. Why tricky question? You could, by observing here, you can tell. You have these G here or not, there's no difference. Does it make sense? But this G is shaded this way, and then you're shading here, and then what the minimum value is determined by circle itself. Has nothing to do with this line. That's why it's 5. That's why the minimum distance now becomes 5. Does it make sense?
What was the X value that you got for this example?
Example 2. Which example?
Oh, the last example we did.
Last example. You mean 3 or?
Yeah.
You mean 3, right? Here.
Yeah.
All right. Jumping back to there. Okay.
Yeah, I didn't.
Wonderful.
I got 16 divided by 3, which is 5.333 for y. I don't know. We're just substituting y equals 2x. Oh, that's a positive there.
Yep.
Okay, I see.
All right. Okay. So going back to this discussion, well, it's different discussion. Okay, and please follow that too. Okay. So here, if the problem is given in black like this, don't worry about it. Okay, it's a tricky question, and it shouldn't happen. It shouldn't happen because this U here is useless. Shouldn't appear there. All right, this is the math. This is the math. The math, and we can now talk about. We can finally now talk about the. No, it's number 4. I think is number 4. Economic dispatch. Of generation. Here, neglecting loss and generator limits. Now we finally go back to the power system class. Okay, we jump from the math 341 back to our ECE 341. Okay. So first of all, you need to understand what we are talking about. We are trying to study the. Well, actually, just find the minimum cost for generation. Find the minimum cost. So from here, you can easily tell the cost is our what? Object function. Second, this objective function, or say the cost function, is modeled as this. Okay, modeled as this. Okay, this cost function is something given, and the modeling of the cost function is not our job. Not our job. At least not in this course. It's very easy. C sub I equals to lambda I plus beta I pi plus gamma I pi squared. Let me explain about them. Okay. First of all, this is the cost. For generator I generating this amount of power P. Okay. Okay, we have subscript I, right? I is representing what? I is here is representing the generator, is the index of the generator. So we have C1 through Cn maybe. That means what? We have n generator. They have different cost function, C1 through Cn. Does it make sense? So this C is referred to one particular generator. It's not the total cost yet. It's not the total cost yet. It's individual generator. Okay, here is individual generator. Individual generator I generating how much power? P. Or say Pi. Indicating this is the amount of power assigned to this particular generator to generate. How much cost it's gonna have. Keep this concept clear. Okay, this is talking about the individual generator I. And how much cost it will have for generating this particular amount of power. And obviously, it's a quadratic equation of the power. And alpha I, beta I, gamma I, they're just a coefficient. Okay. They're just a constant coefficient. Determined by what? By your modeling. Okay. Somehow you model them and come up with these coefficient constants. And this guy gonna introduce capital C sub t, which is equals to now it's not difficult to guess, right? So this is what? What is it? By this equation, this C sub t is what?
Total cost for all the generators.
Very good. The total cost. Okay. It's the total cost for all the generators. All the generators. As I said, from I equals to 1 to up to the number of the generator, right? 1 to the number of the generator. Sum them up. It's the total cost. And therefore, it equals to what? Pretty much you sum these all up, right? Sum these all up. To through from 1 to g. And then about alpha I plus beta I, pi, gamma I, pi squared. Right, this is just a substitute Ci here by the function up here. It's an individual generator. Okay. This is the cost function. Okay, we can leave it here. Cost function here. We're trying to minimize this guy, obviously. Next, after the cost function, what we should discuss? Constraints, right? Constraints. So think about constraints. So what constraints we're gonna actually really taking care? Anyone can come up with any guess, or of course here there are many constraints, but we are neglecting the laws, we're neglecting the various generator limits as well. So who is the constraint then?
Would that be
Very significant.
customers you need to supply?
Very good. Excellent. Excellent answer. P sub D, which is equals to what? Summing up all of the individual generator power. So what this is saying is what? So subscript E is representing what? Demand. So this is the total required power, of course, from customers. It's a negotiable, right? It's a negotiable. Customer asks for 1,000 watt. You are providing that amount. Of course, you do want to provide more. I mean, except concerning the loss, right? Because you don't want to spend more money. But can you provide less? It's not negotiable. It's not negotiable. Asking for 1 kilo, you have to provide 1 kilo. So this is the constraint. This is the most significant constraint. Does it make sense? And what you do is just somehow assign this total number to different what? Generator. That's why it equals to the summation of each generator power. And here, Kevin is asking the proper voltage and frequency as well for constraints, or do those all loss and limits? Well, anyone can answer this question before I provide an answer. I think it's good. It's a good thing. Anyone can answer this question. Any thoughts? Nothing? All right, here's the thing, okay? So-called proper voltage and frequency. Let me explain what does Kevin mean, okay? For generating a certain amount of power, however, you need to generate the power in the format of voltage and current, right? So first of all, your voltage must be what? Certain magnitude. And more importantly, it has to be what? 60 hertz in this country. Does it make sense? You go to the outlet and then receive what? 120 volt RMS value, voltage AC, single phase with 60 hertz, no more, no less. Right? It's not random amount of voltage, not random amount of frequency there. Otherwise, it's going to be a mess. So these are very strong requirements for the generated voltage. Okay. As to the current, of course, you have a voltage source, and the current is determined by the load you're applying on. Okay. However, here we are studying the cost. So we are leaving the voltage magnitude and the frequency to whom? To the control system. We are leaving them to the control system. While meeting these constraint total power, you need to somehow provide decent, or say required, voltage magnitude and frequency. And they are very, very important. That's true. So we're leaving these two controls to the control systems. Okay, they're actually about control, how you control them to happen. And when we talk about money, talking about this, we are talking about power and power only. Okay. All right. So let's move on to here. I think the only thing we need to do one more step here is, if you recall, our constraint function cannot be in this format. So what can we do is we move the summation to the left-hand side of the equal. Therefore, this is our what constraint. Equality constraint function. All right. Because the equality or inequality, we need to what? Compare with 0. Rather than this. Okay. This itself, no, is you can't involve it into the L, big L. So. And therefore, at last, the total what Lagrange multiplier, it equals what? Which is here plus lambda times PD minus, yeah. And if you want, you can substitute this C sub t by maybe this one. Feel maybe better. Okay, the same thing. This guy plus lambda times constraint. This is our big L, total L. And we're gonna find a partial derivative for, right? So any questions? All right, so no questions. I think we can stop here today and leave the rest of the work to next lecture, which will be on Monday. Oh, one thing, almost forgot. There's a thing you need to be very clear. What is the unit of this guy? The cost, of course, also the unit of this guy. They're going to be same unit. Okay. This cost C. What is the unit? Dollar. Any other answer? Money. Yeah, but what is the unit? It's not dollar, not exactly dollar. Anyone have any thoughts? All right, you guys are funny. I give you that, but it's dollar per hour. Dollar per hour. So what does it mean? It means, because power, remember, power is what? The derivative of the energy, right? Versus power times the time equals the energy. You are using 1 kilowatt for 1 hour, or you use 1 kilowatt for 10 hours. It's absolutely different amount of energy. Therefore, different amount of money should be paid. Does it make sense? So you have to involve the time. Okay. I hope it is dollar only. Okay. I hope that way. So, the consumer energy gonna broken very soon that way. So remember, it's dollar per hour. Okay, there's a energy concept behind, and therefore there's time concept behind too. Okay, so dollar per hour is the cost unit. All right. Thank you all for attending today's lecture, and talk to you guys next Monday. By the way, next Monday, what are we gonna do? Actually, there's
I
one
was
thing we
just
need
about to ask that. We're going to review next Monday.
correct. Good. Okay, next Monday we're gonna review. Right. Midterm 2 is upon us. All right. Thank you, everyone, again, and have a good weekend. Bye bye.